All right, today we're going under the hood. We're going to see how databases actually store your data on a disk. And trust me, this is one of those fundamental concepts that can literally make or break your app's performance.
I mean, you've definitely felt this before, right? You run a query, boom, it's instant. Then you run another one that seems almost identical, and you're just staring at a loading spinner, wondering what's going on. Let's unpack exactly why that happens.
Well, the answer lies in this huge gap between what we think a database table looks like and what it actually is on the physical disk. So let's peel back that layer of abstraction. As developers, this is our world, right? A beautiful, clean grid, rows and columns, all perfectly organized. It's intuitive, it's simple, and you know what? It's an incredibly useful illusion, but it's not the truth of how your data actually lives.
Because the moment that data gets written to a hard drive or an SSD, the picture changes completely. That neat little grid is gone.
See, the database doesn't really think in terms of individual rows. It thinks in something called pages. A page is just a fixed-size chunk of storage on the disk. You can think of it like a standardized shipping container. For a database like Postgres, it's usually about 8 kilobytes. And this is the reality. The database just crams as many of your rows as it can possibly fit into each page. And here's the kicker. When it needs to retrieve data, it doesn't just go grab that one row you asked for. Nope. It has to grab the entire page that your row lives in, along with all its neighbors.
So that brings us to maybe the most important concept for performance. If we have to read these entire pages, how do we measure the actual cost of a query? What's the currency we're spending here?
And that currency is I/O, which stands for input/output. Every single time the database has to pull a page off the disk, that is one I/O operation. And let me tell you, reading from a disk is by far one of the slowest things a computer ever has to do.
So this is it. This is the golden rule of database performance. Our entire goal, our whole mission is simple. Minimize the number of pages we have to read from the disk. That's the whole game.
Now, when you put all the pages for a single table together, that entire collection is called the heap. Think of it as the full library of your data. Everything you need is in there, but it's like a library where all the books are just thrown into one massive, disorganized pile. They're all there, but they're in no particular order at all.
So what happens when you need to find one little piece of data in this messy heap? Well, the database has no choice but to start at the very beginning. It reads the first page, checks for your data. Not there? Okay, reads the second page, then the third. This brute force method is called a full table scan, and it is absolutely the villain of our story.
But of course, there's a much, much smarter way to work. And this is where the hero of our story comes in, the index. An index is a totally separate, highly organized data structure. The best way to think about it is like the index at the back of a textbook. Instead of reading the entire book cover to cover to find one topic, you just look it up in the small, sorted index, and it tells you the exact page number you need to go to.
So how does this actually work? Well, it's pretty clever. It doesn't copy all your data. It only stores the value of the column you chose to index, say an employee ID, and a tiny but absolutely crucial piece of information, a pointer. This pointer is the exact address of where the full row lives back in that main heap. And because the index is so much smaller and more organized, it is incredibly fast to search.
So this is the workflow in action. Instead of scanning that huge, messy heap, the database first does a super fast search on the small index. The moment it finds the entry, it uses that pointer to make one single direct jump to the correct page in the heap. It's surgical, not brute force. Okay, enough theory. Let's see the payoff. I mean, how much of a difference does this shortcut really make in the real world? Here's our mission. We need to find a single employee, ID number 10,000, in a table that has thousands and thousands of rows, all spread out across hundreds of different pages. Without an index, we're stuck. The database is forced into that painfully slow full table scan. It starts at page 0, performs an I/O. Is employee 10,000 here? Nope. Moves to page 1, another I/O. Page 2, another I/O. It has to read every single page, one by one, until it finally stumbles upon the employee on the very last one. That is a massive number of expensive, slow I/Os. Now, with an index, it's a completely different game.
The database first just consults that small optimized index. In a fraction of the time, it finds the entry for employee 10,000 and sees that it lives on page 333. Then it performs just one targeted I/O to fetch that specific page. The difference is staggering. We went from hundreds of I/Os down to just a couple. That right there is the difference between slow and instant.
So, look, the big takeaway here is this. It might feel like you're deep in the weeds, but understanding this relationship between pages, IOs, and indexes is the absolute key to building fast, scalable applications. This is truly what separates good developers from great ones.
So we've seen it. The true cost of any query is measured in I/O. It's not about how complex your code looks. It's about how many pages you force that database to read from the disk. So I'll leave you with this question. Now that you know this, how is it going to change the way you design your next table or write your next query?